In the third part of Precalculus Lesson 10, we look at conjugate pairs and the role that they play in complex zeros of polynomials where the polynomials have real number coefficients. This is from section 2.5 in the college algebra textbook. We start with the conjugate pairs theorem that tells us if f is a polynomial function with real number coefficients and a plus bi is a zero of f, then its complex conjugate a minus bi is also a zero of f, or vice versa. Remembering the last lesson, we had f of x equals x cubed minus x squared plus 4x minus 4. And from that polynomial, we found zeros of 1, 2i, and negative 2i. Notice here that 2i and negative 2i are complex conjugates, and also note that f of x does indeed have real number coefficients. We also had f of x equals 3x to the fourth minus 22x cubed plus 55x squared minus 46x plus 10, where we found zeros of 1, 1/3, 3 plus I, and 3 minus I. Again, this polynomial has real number coefficients, and it has complex conjugates as two of its zeros. Now we're going to create a polynomial p of degree 3 with zeros x equals 3 and x equals 2 plus I that has real number coefficients. Well, for this to be true, we need the complex conjugate of 2 plus I to also be a zero. So that would be x equals 2 minus I. And now I'll set up my polynomial. P of x is going to be equal to some coefficient of a times x minus 3. Remember, if 3 is a zero, then x minus 3 is a factor. 2 plus I is a zero, so x minus 2 plus I is a factor. 2 minus I is a zero, so x minus 2 minus I. Let me fix that. Hold on. 2 minus I is a zero, so x minus 2 minus I is a factor. We'll simplify to get a times x minus 3 times x minus 2 minus I times x minus 2 plus I. So I'm going to start by multiplying x minus 2 minus I times x minus 2 plus I. We'll begin by distributing this x through, so we have x squared minus 2x plus ix. We will then distribute the negative 2 through to give us minus 2x plus 4 minus 2i, and then the negative I, so we have minus ix plus 2i, and then minus I squared. Okay, moving on, a times x minus 3. Note that we have a few things we can cross out here. Ix minus ix adds to 0, and negative 2i plus 2i adds to 0. So simplifying here, I have x squared minus 2x would give me minus 4x, then plus 4 minus I squared. That's the same as minus negative 1 or plus 1. So I have 4 plus 1, or plus 5 here. Then we'll multiply x minus 3 by x squared minus 4x plus 5. We have a times, first distributing the x through will give us x cubed minus 4x squared plus 5x. And then distributing the negative 3 through, we have minus 3x squared plus 12x minus 15. And we simplify again to get x cubed minus 7x squared plus 17x minus 15. So I have my polynomial with this a out in front of the factor containing x cubed minus 7x squared plus 17x minus 15. Well, a could be 1 as easily as anything. We're not given any specific requirements for this polynomial that would require a to be anything else. So let's just let a be equal to 1, and we will end up with a polynomial of x cubed minus 7x squared plus 17x minus 15. If you think about it, there's a lot of other polynomials that would meet these requirements here, but this one's as good as anything for now. Okay, moving on to creating a polynomial p with real number coefficients again that has zeros of negative I, 2, and negative 2. So with real number coefficients, we know that we also have to have a 0 of x equals I, the complex conjugate of negative I. Additionally, this polynomial is to have p of 3 being equal to 25. So let's work on creating a polynomial p of x that is equal to, if negative I is a 0, then x minus a negative I, or x plus I would be a factor. Oh, I forgot to put an a here. So there's an a out front here. If x equals I is a 0, then x minus I would be a factor. If 2 is a 0, then x minus 2 would be a factor. If negative 2 is a 0, then x minus a negative 2 or x plus 2 would be a factor. So we have p of x equals a times x plus I times x minus I. We can FOIL to get x squared minus ix plus ix would add to 0, and then we have minus I squared here. Excuse me. And x minus 2 times x plus 2, we would have x squared minus 2x plus 2x adds to 0, and then minus 4. So we will next multiply x squared minus I squared, which I should say is x squared plus 1. I squared is negative 1, so x squared minus a negative 1 would be plus 1, times x squared minus 4. We multiply together to get a times x to the 4th minus 4x squared plus 1x squared would give us minus 3x squared, and then minus 4. Okay, so I'm almost there, but I do have another requirement on this polynomial, and that is that p of 3 equal 25. So let's make sure that p of 3 equals 25 here. What I can do is plug in x equals 3 and y, or p of x, equals 25. And that should give us a solution for a that would meet these requirements. So let's have 25 equals a times 3 to the 4th minus 3 times 3 squared minus 4. And so 25 is going to equal a times, this would give us 50. So a equals 1/2. Okay, so plugging in a equals 1/2 to our polynomial, we end up with p of x equals 1/2 times, I'm looking right here, 1/2 times x to the 4th minus 3x squared minus 4. And just to make that look nice and clean in the end, let's write this as 1/2 x to the 4th minus 3x squared. Whoa, okay, I messed that there. Let me fix that. Minus 3/2 x squared. And then minus 2. Okay, so we've got it. Now, last of all here, try on your own. Number 3 is to create a polynomial p with real number coefficients that has degree 4 and zeros of 1 minus 2i and 1, such that 1 is a 0 of multiplicity 2.